All right, so how you guys doing on
Good.
Monday? It's good?
Good.
Perfect. So once again, just want to remind you we have an exam coming next week. So I'll finish up the lecture today before exam one, and I'm gonna spend about full three lectures just for the reviewing the material. Meaning, I'll give you just a problem, and we'll try to solve the problem together. And the problem will be quite similar to what you're gonna see on the exam as well. It won't be 100% the same. Maybe some of them will be, but it will be similar anyway. Okay? So before we, so we'll do the review session. Today, technically, we finish up the chapter 5, so we can do the review session starting from the Wednesday. Okay. So the last part of the chapter 5, there are only a couple more things I want to mention. So, you guys remember we talked about the Meso compound, right? Meso compound. So Meso compound is the one that has chiroid centers. They do have chiroid centers, but they have a symmetrical plane in the compound, so they become achiral, meaning it's not chiral anymore. Even though it has chiroid centers, Meso compound is the one that is still achiral because it has a symmetrical plane. They're same on the the other side of the symmetrical plane. So it makes sense, right? So this is the last thing we talked about on Friday. Okay, Friday. So if that is the case, there's a couple more things I want to mention about the chiroid center. I drew this one actually a bit lower here. Okay, this one. So we talked about the chiroid center. So if you look at this one, can you guys name this real quick? It would be methyl cyclohexane because it's 6 carbons. Okay, so methyl cyclohexane. If you look at this one over here, you always need to assume there's hydrogen implied there because we don't normally show the hydrogen on the compound in organic chemistry, but there is one because carbon should have 4. So if you look at this one over here, methyl cyclohexane is the achiral because this carbon here is the 2 hydrogen, 2 hydrogen, 2 hydrogen. So they are not chiral center. There's 3 hydrogen, but this one is still not because it has a methyl group over here and hydrogen. Okay, that's good. But from here, even in ring structure, you can also count it for this chiral center or not by just looking at how many or what type of R group I can say, like a Q groups on each side here. So if you compare these two all the way down to the other carbon here, they're same. Okay? So this is still not chiroid center. So this methyl cyclohexane is achiral because they don't have any chiroid center. Even if you look at the one attached to the ring structure, you can still do the chiroid center check, but still same. So it's achiral. Okay? But if you look at the this one instead, this is 1,3-dimethyl cyclohexane, right? Because you have a 2-methyl group here. So on your exam, I wouldn't even tell you if it's methyl group because you should know by now that it's just 1 carbon. There should be 3 hydrogen automatically. But anyway, in this case, this is the methyl group over here, right? And this is also hydrogen implied there, which I will not show you in the exam. But there's 2 different groups here, and now this carbon can compare to this side and this side, right? So think about it. So this is methyl group here, hydrogen, and this side, this is the carbon in the ring structure are different now, right? Because they were the same here. It's different now, right? So that makes this carbon has 4 different groups there. Okay? So that is okay to say this one do have a chiroid center. Okay? This is chiroid center. So for the same reason here, this is also a chiroid center. Okay? So the point is, you can also do the chiral center on the carbon in the ring structure. That's okay. If you can do this side and this side is different, you can consider these two as a different R group as well. So that is a chiral center. So if that is the case, let's look at a little bit more in detail. Okay. So if I give you this one over here, okay, this one will give you here and here. Okay, so this is chiral center here and here, right? But this will be still achiral in whole. So they do have a chiral center in here, but as I told you before, it's symmetrical all left and right, right? You see that, right? It's the symmetrical. So in this whole compound still behave like achiral. I will not show you any chiral compound characteristic there because it's a meso compound. So this is also a good example of meso compound with a ring structure. Even though you have, yeah. Makes sense, right? This is symmetrical. This is a ring structure. You can have a chiral center, but this symmetrical, then it's still meso compound, so it'll be achiral in a whole compound. So let's do a little bit more on the other. Okay? So let's have a more specific cases for those. So maybe we can have maybe right a little bit lower. Okay. This one, okay? We have this type of compounds over here. And if you try to draw the mirror image over here, this will be looks like this. Well, I'm gonna draw it this way. Yeah. Okay. And then here will be hydrogen. Here. So in this case, you're going to have what? You're going to have enantiomers, right? Because it's a mirror image to each other, right? So whatever you do RS configuration over here will be all inversion over here. Okay, makes sense, right? Because the if you make a mirror image which is enantiomers, whenever you find out the configuration over here, there will be inversion over here. So if you do, this is 1, 2, 3, and 4. Okay? We use the Cunningham-Prelog convention. So oxygen is number 1 because the atomic number is higher than those two carbons over here. These two carbons are in tie, but this carbon attached to oxygen, hydrogen, carbon. And this one has attached to hydrogen, hydrogen, hydrogen. So this will be slightly prior to this one because it's higher in atomic number in oxygen, carbon, hydrogen attached to this carbon than the ones of this carbon. So this is 2 and 3. But the problem is your hydrogen is up front. So you need to look at the Cunningham-Prelog convention when you put the number 4 on the back. So we have a this way rotation here right now, 1, 2, 3. So this is actually R, right? 1, 2, 3. So if you go clockwise, it's R. But because of this sticking up front, so it's actually it has to be looking at the other side. It turns to S actually. Okay. So if you do have a this chiral center S configuration, when you do the mirror image to there, it's automatically R. You don't even need to do it. It's just if you do it, it's just R. Okay, if you look at this one, 1, 2, 3, counterclockwise will be S, but this is still heading forward, so it turns to R. So if you do the mirror image, you can double check, but you don't have to do this because it will be inversion of the RI's configuration with this mirror image teacher. Make sense, right? Perfect. All right. So if that is the case, what if I change this one to here? I change this one to here. Like this, okay? If I change this one to here and here. And then if you look at this one here, this one has the hydroxy group, hydrogen, hydroxyl over here. So this one has this is only the same part here, but those all chiral centers should be different, right? So in this case, which you can call this this is only saying that all three are different, right? So in this case, we're gonna call this diastereoisomers. I want diastereomers. Okay. So meaning is there's only there are several numbers of chiral center, but they're all opposite. That makes the compound enantiomers because it's all different on the opposite side. But only few out of all chiral center, or few, maybe 1, 2, or 3 out of 5 or 4 or 6 chiral center, that makes those two are diastereomers to each other. So they have the same R or S configuration on certain chiral center, but only few, 1 or 2, are different. Then they are diastereomers to each other. Okay, like this. Make sense? Because they have the same chiral center here, but all different 3. Okay, does it make sense? Okay. And also, if you have only one chiral center, is different from other like 4 or 5 chiral center. Do you guys remember this? We call them epimers. That is also one type of, we call that epimers. We call that so epimer is also one type of diastereoisomer. So if you say that's still diastereoisomers, that's still okay to say, that's the correct answer. But if you know that more specifically, you can also say epimer would be better answer there. But still, you can answer them as a diastereoisomers. That's fine by me. But I just want to tell you that is more specifically epimers. If you have only one chiral center, it's different from another, but all the other are the same. That would be kind of almost, yeah. I'll stop here. But this is a type of a thing you can do here. So let me erase this one real quick. And then if you look at this one now, so this is one we compare to the other that makes this compound diastereoisomers. But if you look at this one over here, okay? If you look at this one over here, this one, even though you try to make your mirror image to the other, okay? If you draw the mirror image to this one, this one, okay, try to draw a mirror image. Okay. So these two are enantiomers, right? So it's a mirror image, right? They're not. Because it's symmetrical on here. So if you just rotate it 180 degrees, it's the same. It's the same compound actually. Because if you just rotate it 180 degrees, it's the same. Because it's symmetrical in the middle. So this is still not enantiomers, but the same. So we call them also meso compound. Guys, remember that? We just talked about that too, right? So it's tricky, right? So first thing you really need to think about on the compounds that has several numbers of chiroid center. You need to think about if there's any good symmetrical plane that makes this compound symmetrical on that plane. Then, even though you draw the enantiomers, which is mirror image of the compound, will still be the same compound. Then we can call them meso compound. It's still be achiral. So there will be no mirror image to that compounds. Even though they do have a chiroid center, that's kind of tricky one. Kind of makes sense? Okay. So I promise you, when we do the review, we'll do more. We'll do this in the practical problem. So you actually see more, a more practical way. So don't worry too much, but I still want you to remember what they are really in terms of the definition and what it is and sort of thing. You can get some idea. It will be helpful for you when you do the review session, doing the problem together. It will make more sense. Okay. All right. So let's move on. So there's only I think 2 more things to go. Just 2 more. Okay? So we have only 2 more to go. So I think this lecture will be a little bit shorter than usual. So there's 2 things I want to cover, but those 2 I just want you to remember the definition of it. You don't have to know about how you're going to use it or anything, because we're going to do it in the later chapters anyway. Okay, we'll do have a specific example of those 2. So don't worry about these too much. Once again, for the exam 1, I just want you to remember the definition, memorize the definition. Okay. So the first thing I want to talk about is racemate. Racemate, or you can call this racemic mixture. Okay. So the racemic mixture is the kind of a reason why we did for optical property. Optical property. You guys remember dextrorotatory or levorotatory? They rotate the polarized light in a certain degree. You guys remember this? This is related to this one. This is now how you can use this one real quick. So if you have any R configuration compound, and you have an S configuration compound, this is the same. So probably you can do this compound, maybe easy example here. Okay. So this will be 1, 2, 3, right? This one is R. Okay. And then this one has so it would be 1, 2, 3, but this is up from you to do. So it goes this way, but this is number 4 is going forward. So looking at the other side, it's going this way, so it would be S. Okay. So you have R and S. This lactic acid, just 2 compounds. If you have these 2 compounds mixed exactly 50%, we call them racemic or racemic mixture. This is the only thing you have to know. This is important in the organic chemistry because if you have these 2 may have optical property, right? Because it's R or S configuration. But if they mixed in the mixture, like for example R compound and S compound, or 50% equally mixed in the mixture, even though these 2 R and S compound has an optical property, they can rotate in here and here. They rotate the polarity right in the same degree but the opposite directions. So if you have a racemic or racemic mixture, even though they are a mixture of the compounds that has what? Some chiroid center and also have some optical property, they cancel them each other in the same degree, so there is no optical property there. So if the light goes in, there's no change of the degree. So does it make sense? So even though the compounds rotate the polarized light certain degree, right? If it's R and S, they do it in opposite directions. So if you turn the 10 degree to the right, If the other one rotate the light on the 10 degree to the left, you're still on the same position, right? So if that is a 50-50% with the R and S configured compounds mixture, we call them racemic because they will show you almost no optical property. There's no change. Even though each individual mixture, the compound will have optical property, because of their RS inversion configuration half and half, that makes almost behave like there's no optical property. This is the only thing you have to know. That's it. You don't have to know how to apply the chemical reaction. No, not yet. We'll get there soon after example. Okay? Makes sense though, right? So racemic or racemic. So don't. It's kind of weird pronunciation, but it's racemic or racemic mixture. Just the 50-50 that makes this mixture as shows almost no optical property, even though they do have each, but mixed same degree cancel out this one. Okay, that's it. And then there's one more thing. One more thing I want to put in is the prochiority. Prochiority is there's just some. There's no chiral center yet, because you see this carbon has 3 hydrogen. It has only 3 bonds here, 2 and 3 hydrogen. So there's no carbon that has 4 different bonding here. But you don't have to know yet. We're gonna do some reduction here. We're gonna do some reduction reaction in the exam 2, after exam 1, and then you can actually do chemical reactions. Chemical reactions here. We do several ways to do it, but we mostly it's done by reduction. And then when you do this, you can do this one. Okay, this way. So you can. So there is one chemical reaction here, and that makes this compounds to be this one. And now you have a chiral center here. You have a hydroxy group here, ethyl group, methyl group, hydrogen. So now you do have a chiral center after one chemical reactions here. So prochiority, or you can say this compound is a prochiral. When you can have chiral center after one step of chemical reaction. So one single chemical step makes this achiral compound to be chiral compound. That position or that compound you can call, or it has prochirality or prochiral. So it's not yet chiral yet, it's just achiral. But after one single step of chemical reactions, it can be chiral. So the prochirality, like pro, simply means like a potentially, it can be a chiral, but not yet. But one simple single step of a chemical reaction make this compound to be chiral compound, which they will have a chiral center in there. That is what we mean by, this compound is prochiral, meaning it's still achiral, potentially easily to be a chiral compound after single step. That is the most important thing, is a single step. Just one step makes the chiral, then we can call them prochiral. Because if you do lots of steps of chemical reaction, obviously you can make a chiral center for everything. But that makes only one single step, can be a chiral compound. We can say, this compound is indeed prochiral, you can say. Makes sense, right? Okay. So we'll learn about this one maybe next month or next month. How are we gonna do this? Don't worry about it yet. Just for what it is. Okay. All right. So that's true. Maybe okay. Maybe do you have I'll just stop here today.